Okay. Hi guys, can everyone hear me? All right, cool. Hi guys, so I'm Omer. As Vishnu mentioned, I'm a compiler enthusiast, aside from being a functional programming geek, and I work as an iOS developer at Garena. So today we're going to be talking about dragons, right? In particular, we're going to be talking about this dragon. Has anyone seen this dragon before? Anyone? All right, good. Those of you who say you haven't seen this dragon, you're lying because you have. This guy, you all use this, right? So Xcode, if you use Xcode, you've definitely seen this dragon. And my aim today is to teach is to tell you guys how you can tame this dragon so suavely, with such swap that you look like this guy, like when you're dealing with this dragon. For those of you who don't know what I'm talking about or don't get the joke, it's okay. Let me define LLVM for you. What exactly is LLVM? LLVM is a collection of modular and reusable compiler and tools and technologies. I copied that from Wikipedia, so it might not make much sense. But let me explain a bit more. And for those of you who are wondering why I'm not talking about a real dragon, guys, this is a compiler talk, chill. We do dragon jokes all the time. But just to give you an idea of what is LLVM and where it comes from, we need to go into compiler 101. So we're going to talk about compiler phases now. All right? And when it comes to compiler phases, there's this flow chart that some of you who studied compiler design might have seen before. It's quite common. Looks like this. This thing really turns me on, actually. But for most people, it doesn't. For most people, this thing is what exactly is going on? But let me summarize. For all these steps that happen in a compiler, there's two main steps. The first step is a front end. A front end will transform your source code into an intermediate representation. And you have a back end. The back end will transform that intermediate representation into machine code. So in compiler phases, in this flowchart, the first three steps, roughly, are your front end, which includes the Lexing, parsing, and your semantic analysis. So where does LLVM come in? And how does LLVM help us to fix this problem? If you're using LLVM, this is what compiler design becomes, essentially. You just have to do three things. You need to do Lexing, parsing, and you need to basically do your semantic analysis to construct a compiler. And LLVM has your back end covered. All right? So this is just so much better. All right? So what exactly is LLVM? LLVM is actually a very powerful, reusable compiler backend. So if you're designing a new programming language, you can reuse this backend to target all the architectures that LLVM already supports for free. So you don't need to implement your own machine code for ARM or PowerPC or Intel or whatever. So, and it's quite popular these days. So there's a lot of compilers using LLVM. Our beloved Clang, for those of you who still use Objective-C like myself, and use C or C++, Clang uses LLVM under the hood. Rust, for those of you who've tried it out, also uses LLVM. Haskell also uses LLVM under the hood. And finally, our beloved Swift. And there's a lot more. A lot of new languages are using LLVM under the hood to abstract out the compiler backend to target multiple architectures. So, warning, I'm a lover of history, and I'm going to give a long and winded history lesson. So be warned, it's okay if you fall asleep. Clang started as a university project by this guy, who's very famous, Chris Lattner. He started as a PhD project, and now he works on it at Apple, and he's a rock star. He's quite awesome. So the lesson here is that if you do a good FIP, you can get hired by Apple, and you can be quite famous. So that's the end of my history lesson. Now let's go to the gist of it. How does LLVM exactly do it? How is LLVM such a good backend, and why do so many compilers use it? The juice, or the main ingredient behind LLVM, is LLVM IR. That is LLVM internal representation. And if you think about LLVM as a function, right? LLVM as a function will be a function that takes LLVM IR and converts it into machine code. That's all LLVM does. So you don't need to worry about it. All you need to do is to provide it with LLVM IR. All right? So what exactly is LLVM IR and how does it look like? Let's look at that next. So I came up with the simplest C code that I could possibly come up with. So I have a very simple C program here. It just defines a function called main, and it returns 42. It can't get simpler than this. All right? I'm going to show you the LLVM IR that this thing emits. And to do that, I run this command, clang with emit LLVM, and I get this. So this is LLVM IR. So what exactly is happening here? This, first of all, we are defining a function called main, and this function returns something of type int32, and inside the body of this function, we have a return instruction, which also returns something of type int32, and it returns the constant number 42. So notice one thing, that the all the instructions have a type definition on them, which is awesome. All LLVM IR instructions are type safe, and this is a very good advantage which helps in a lot of optimizations later on. So let's look at a slightly more complex example. Let's say I have this Swifty looking code where I say my variable C is equal to A plus B. What will this look like in LLVM IR? It looks something like this. So I have an identifier, variable, label, whatever you want to call it, this variable called %C, which is equal to the add instruction, which adds something of type int32, %A and %B. %A, %B are also labels and variables, so it's quite straightforward. Basically, this is just an add instruction, and it'll assign the result to C. What this actually maps to are register assignments at a CPU level. So when LLVM will compile your code, it will actually convert these assignments to register calls. So a few things about these variables. Anything that's prepended with percentage is a local variable, so it cannot be modified outside of the scope that is defined. The other thing is, so as I mentioned earlier, these locals represent register assignments. So here's another example. I have this percentage result is equal to multiply this thing by x. This will be translated into a CPU instruction whereby you will assign registers, so you move AX, then multiply something into AX, then move BX, DX, etc., etc. Another thing is that you can have infinite number of registers or variables inside LLVM IR. This is very helpful. If any of you have done assembly language before, or written like raw machine code before, generally you will only have 4 registers or 8 registers available to you. In this case, LLVM will abstract that out and will handle the register assignment itself. So it gives you an infinite list of variables. And on your side, when you're coding, when you're emitting LLVM, you don't actually need to worry about conflicts either. It will handle conflicts by itself. So, that done. Similarly, we're just going to look at one more example of LLVM IR. Function calls. How do we handle function calls? Here I have a let statement where I just assign 3 to the result, add 1, 2. This will be translated into something like this. So I have this thing, I have a call. This thing is equivalent to a function call, and then I call this function define call at A, and then pass it these arguments. All the return types are double in this case. All right. So there's loads of instructions. I won't go through all of them naturally, but this is actually all we need to define a very simple language. All right. So what is the language we're going to define today? This language is called Cisp. It can stand for Swifty Lisp. It can stand for Sucky Lisp. It can stand for whatever you want. Sexy Lisp, maybe? Sexy Lisp. But yeah, anything. It's going to be a Lisp. For those of you who haven't dealt with the Lisp before, I'm sorry. I apologize in advance. It might not look nice. Anyways, I choose this language because it's very simple. There are just 4 constructs in this language. All right? The first construct are numbers. Numbers evaluate themselves. So if I have a number called 42, it'll evaluate to 42. And just like JavaScript, we only support doubles. All right? No integers, no Boolean, everything is a double. All right? Just keep things simple. All right? So then the other construct we have are predefined binary operations. So I can define these predefined functions. So I can define add, for example, the plus sign. And this one is predefined, and this thing will evaluate to 7, for example. So I have a bunch of predefined operators that are hard-coded. These are all your mathematical operations that operate on doubles. Okay? Next thing, the third construct, I can define functions. And this is how I define a function. I'm sorry for those of you who haven't used a list before. I apologize again for the parents. But the way we define a function is we use this thing called defin, the function name, and then the arguments, and then the function, this thing is the function body, in which case we're doing an add. All right? It's pretty straightforward, I hope. Lastly, is function calls, which is the same syntax as the binary operator, just that the number of arguments depends on the function you're calling. All right. That language is done, and I'm sure everyone's clear with how the language works. It's quite simple. So now we're going to implement the compiler for this language. How do we do this? We have the 3 commandments. As I mentioned, the 3 commandments are lexing, parsing, and emitting, right? So what is lexing? And what's the first stage? Lexing, when we're talking about lexing, we mean we're going to convert this string into something called a token. Now, some of you are wondering what the hell is a token? How is it different from a string? I think for these kind of things, right, it's just easier to show you the code. So I'll just show you the code. Since I implemented this in Swift, my code is in Swift. So the way I define a token is I have a struct called token. This thing has a type. And I only support these types of tokens. A token can be a parentheses, open or closing parentheses. It can be an operator, it can be a number, or it can be a name. All right? And this string val contains the string content itself of that token. So if it's a name, it'll contain iOS conf, for example, the whole string inside. And I will define a function called tokenize. Tokenize will take input string, and it will return to you an array of tokens. All right? That's it. That's all that tokenize does. So it'll convert that string into this token. And to just take a look at how it will work, let's say I call this tokenize on this input. This is my input, plus add 4 to A. All right? Then the first token is the opening parent. The second token is the plus. Third token is 4. Last token is A. So as you can imagine, the implementation for this is quite simple. It's quite straightforward to implement, so I won't go through the implementation. You just need to iterate through the string, gather all the till all the tokens, and just generate this. It's quite straightforward. We won't go through it in detail. So that's for tokenizing. So far, so good. The next step is parsing. Parsing means we convert tokens into an abstract syntax tree. Once again, abstract syntax tree, to people who haven't heard of it before, might sound scary, but it's actually very simple. And it's something that if I show you the code, you'll be like, oh, this is what it is. So what exactly is an abstract syntax tree? For this language, I will show you the abstract syntax tree. It's just a Swift enum. This Swift enum has the following types. The first thing are my constant values, the 2 trivial cases as I call them, where I can be a number. So if I'm a number, it'll contain the value inside my number, which is in this case, for example, this example 42. It can be a name, which would, in this case, iOS conf, for example. It can be a binary operation, where if you notice, I have this, where I have my operator, which is a string. Then I have my left-hand side expression and my right-hand side expression. So this thing is recursive. That's why I need to use the indirect case. These are the basic things I need to define for just my binary operations to work. To add function support, I just define 2 more enums. I have a function call where I will define a callee, which is the name of the function you're calling, and the list of arguments, which is an array of expressions, which are going to be which you're calling with. And lastly, you have the function itself, which contains a prototype and a function body, which is an expression. And a prototype contains the function data, which includes the name of the function and the argument names. That's all. All right? This thing is an abstract syntax tree. Like, it's not that hard to visualize how this will work, right? Like, for example, if I if I provide this input, where I define an add function, the tree that I will generate will look something like this. I will have a function with this prototype, name add, args this, and inside I will have a binary expression, and inside the binary expression I will have a name expression, 2 name expressions, right? That's it. It's just a simple. So that's all that my parser has to do, okay? And you can imagine the implementation of this is not so difficult to do actually. There's a few ways to implement a parser. One of the ways is you can handwrite it yourself, which is what I did in this case, with handwrite a recursive descent parser. You can use parser combinators, which are very fashionable these days, but I'm not going to go into that because I don't have enough time. Or you could use a parser generator, which will generate parsers for you, and there's some very mature libraries out there to help you do this. In this case, we're going to write our parser ourselves. So how are we going to implement the parser? We're going to define a function called parse expression. A parse expression will just take an array of tokens, and it will return to you a parser result. And a parser result just contains the expression that you parse, the result, and it contains all the remaining tokens that you haven't parsed yet, so that you can pass this result around, and you can recursively parse stuff. And just to give you an idea, I'm not going to go through the full implementation, but just give you the gist of the idea of how it works, is we're going to do a pattern match against the first token, because you get a list of tokens. You can do a pattern match against the first token. And we have the 2 trivial cases. The 2 trivial cases are, if you're a number, then you just extract out the number from the token and make an expression out of it. So if you're a number, then I make a double expression out of it. If you're a name, I just make a name expression out of it. This thing is trivial. Similarly, if I have an opening parentheses, then I can either be a binary operation if my token type is opt, or I can be a name. If I'm a name, then I have some predefined names like defin and if, and other than that, if you're not either of those, then you are a function call. So you can write these. You can imagine how the implementation of this thing is going to look like. My point is, it's not that complicated. You can figure it out. I'm not going to go through the full source code. But I have put this full source code on GitHub. I'll pass you guys the link later. So this part is fine and dandy. We haven't touched LLVM yet. So where does LLVM step in? Well, this is where LLVM. This is how LLVM will step in. Yay! Import LLVM. We're done, right? Sadly, okay. Awesome thing is LLVM provides a C API for you to implement LLVM IR and for you to generate LLVM IR, which is awesome because LLVM itself actually is written in C++, which you can't use in Swift. Sad thing is that getting this to work is slightly tricky. First thing you need to do is you need to compile LLVM from source. Second step you need to do is to wait for the first step to finish, which can take a very long time. Like this took me, I think, I set it to compile one whole night, and by the morning it was finally done. The third step is, oh yeah, you guys mentioned compile time of 7 minutes. Take that, man. like this thing is a big project. All right, the third step is you need to add the header and library search paths, which is fine, not so hard again. Fourth step is you need to find you need to use this tool called LLVM config to find all the libraries that you need to link with when you build it. And this thing is tricky because it doesn't mention all the libraries you need to link with. So you need to fix all the missing linker errors. This takes a long time. Trust me, I found that setting it up is harder than implementing it actually, like a lot harder. So after this entire jumble and after figuring out all these linker errors and hoping you find hoping to get it to compile, when you get the import LLVM to compile, you're going to feel so good about yourself. You're just going to stay, okay, that's it. I'm done for the day. All right? But not yet. Now for the easier part, the code generation, which is actually quite easy compared to setting up LLVM. Code gen. How will code gen work? So for code gen to work, I'm going to define a very simple method. It takes an expression and a context object, which contains all the necessary globals that I need. And it will return to me something called an LLVM value reference. This thing is a type defined by LLVM. So let's just take it for what it is. My context object, I keep track of my what I call my named values, which is the symbols that are defined in scope so far. This thing is a mutable dictionary, so I can change it every time I code gen. And we have this thing called a builder and this thing called a module. You guys have heard of Swift modules, right? A Swift module is roughly the same thing as an LLVM module actually under the hood. An LLVM module will basically is a compilation unit, and it will define the set of symbols and set of functions that are defined, that basically will be defined within that module. Then if you want to import modules, like you'll import the module and then those symbols will be available to you. And builder is just this reference you need in order to build instructions. So once again, for code gen, we're going to first deal with the trivial cases. The trivial cases being the number and name. For number and name, very simple. For number, it's very simple. If I see a number, I know it's a constant value. And because in LLVM, of course, right now in my compiler, I'm only supporting doubles because doubles are awesome and they're all that you need. And JavaScript says it's okay. So I will use this thing, LLVM constant real, to generate a double. To this thing, I provide the type I'm using, which in this case is double type and the value. So this thing is simple, right? If you see a number, you generate the constant. If you see a name, like I see iOS Conf in my expression, I don't know what the value inside is, but like I mentioned, my context is keeping track of all the value of all the values in scope. So I'll just get the value in scope. Naturally, in the actual code, I have some error handling and stuff here, which I didn't mention here for brevity's sake. Next, binary operation. How do we generate binary operation? This is where it looks kind of pretty, right? Like, if I have a binary operation, then I will first code gen the left-hand side, I code gen the right-hand side. So these things contain the LLVM values. And then I will just build an instruction with those LLVM values. So in this case, for example, I just show one instance of it. If I have an add instruction, I see add, I will build fadd. Fadd will add a floating point add instruction. And I will provide the builder object, and I'll build it with these two values provided. And I'll give it some placeholder name. You don't need to worry about the name having conflicts because LLVM will handle that for you. So yeah, and you just rinse and repeat this for other operations. Quite straightforward. So far these two cases are quite simple. What about functions? How do we code gen functions? Right? For functions, the way LLVM works is that we first need to code gen the prototype, the header of the function. In which case, for every LLVM function, you need to define its type, and you need to define the arguments that it takes. So for the first thing we do is we define the function type, which for all functions, yay, double to double, right? So all functions return a double. That's why my return type is always double. My return type is going to be double. And I'll just, basically what I'm doing here is that I will iterate through the arguments to set the argument names based on so when I have add A, B, I know A and B are the argument names. So I use this LLVM set value name to set the argument names to A and B. And I just return this function. In LLVM, we have this concept of a basic block. It's just not this concept to LLVM, it's a generic compiler design concept, where a basic block is simply a container of instructions that will execute sequentially, and the last instruction will have a return, or will basically stop the execution. So in LLVM, everything is a basic block, and a well-formed basic block is that you have a list of non-terminating instructions followed by a single terminating instruction. And the way we implement functions is we're going to use a basic block, and we're going to have all the instructions, and then we're going to return something from there. All right. In our language, all functions return something. Okay. So the way function will work is first of all, I will code gen the prototype of the function, so I can get the name of the function done. I can get the argument names nicely done as well. The next step I will do is I will define an entry block for this function. So I define this. This is the new block, the new basic block that I've started. Then before I start every function, I will remove everything from scope. Then I will add all my arguments to scope. So I will find the I will find the values for all the function arguments using LLVM project APIs for you to get the parameter arguments one by one, and I will add them to scope so that when I code gen my body, in my body I can reference those values easily. Then I will just code gen the body and I build a return instruction to return the result. That's it, done, right? So at the end of all this, relatively simple implementation, what's going to look like is this. So if I define my function add, it's something like this. I take something from type double, I return type double, this is the function name, return the argument types, and all I'm doing is I define this instruction, I call fadd with the two arguments, and I return the result. That's all. That's quite a straightforward implementation, right? Okay, so if some of you noticed, my programming language is actually very useful because I don't have any control flow. My programming language is like it's a pure programming language. There's no if statements, there's no for loops, nothing at all. So it's very, very useful, right? We can use it for daily work. So if you want to add control flow, things become slightly tricky. And the reason they become slightly tricky is so far, or if you notice, we don't have any branches. All our instructions go one by one. We have a set of instructions, then there's return. Another set of instructions, then return, and that's it. And then for all function calls, right? There's no branching here and there, which is something we need to be a real programming language. I wish it was not so, but sadly is so. So how do we add branches? I'm not going to show you the implementation for it, but I'm going to show you what LLVM will produce, and we're going to work through back from there. So for LLVM, if I define, let's say I define this function. Whoa, I'm sorry for this wall of text. I apologize in advance. But let's go through this like slowly. Let's say I define a function is1. In which case, the gist of it is you can ignore all this stuff for now. The gist of it, the focus that I want to focus, the thing I want to focus on is this thing, phi. In order, this thing phi is a special instruction that LLVM defines for you to implement if conditionals. The reason we need this is because, remember, like I previously mentioned, registers are immutable. You can't change their values after you declare them. So, to be more precise, LLVM itself is an SSA-based representation. SSA means static single assignment. So, this means that all registers are only assigned once, and all register values are defined before use. So we can't change the values in between. Because normally how you would implement branching is you would have a register, then you would change its value, right, to something else if you want to do a jump. But in this case, we can't do that. And the reason LLVM uses this representation is because it allows several optimizations to be quite easy. So the way we implement ifs is using this phi instruction. And what a phi does is a phi will remember which block the control came from. So in this case, what will happen is that if my return type, if I jumped to this instruction from this label, then I will have this value inside here. If I jumped to this instruction from this label, I will have this value inside here. So it's quite simple, right? It's basically we'll set the return type of this, we'll set the value inside this register to whatever the context, whichever label you actually broke from, whichever label you returned from. So this allows you to do pretty complex control flow mechanisms. So Cisp is quite sucky. Even if you add ifs, is quite sucky. There's no mutable variables, no lambdas, no IO. There's shitty syntax to those of you who don't like Lisp. But the point that I'm trying to make here is that LLVM is not hard. Recently I saw this, like LLVM is a little pony, which makes sense because it's not that scary actually. You can actually tame this dragon and it's usable and you can use it to build pretty cool stuff. Which brings me to the last part. Why would you do this, right? Why do you care? Compilers work, they work fine. I'm not going to make a new language anytime soon, so why should I even bother with this? I mean, aside from making your own compiler, you can do other cool things, like you can contribute to Swift, for example. If you want to contribute to Swift, Swift is always looking for new contributors, and you can always find an issue to work on, and since it's implemented in LLVM, it really helps to know how it's actually implemented. Also, you can implement better tooling. Xcode sucks, we all know, for Swift. I mean, only for Swift. For Objective-C, it's awesome. But we can actually improve it. If it were open source, we can improve it. But like, we can improve the tooling at least, so we can add more tooling to it if we know how the whole compiler toolchain works. And that's why I find this pretty fascinating. So with that, I come to the end of my presentation. Any questions, feel free to ask.
Thank you. Okay, any questions? Any questions from anyone?
Sorry, I didn't understand your question. Can you repeat again?
Does LLVM work if you want to implement the compiler for dynamic language?
Yes, it does. I mean, if you look at it, my language is dynamic, actually. Because if you notice, I don't have any types in my language. I don't have a type checker, right? The difference between a dynamic language and a static language is just that you have a static language has a type checker that will type check your stuff before it compiles. Actually, a dynamic language still has types. It's just that it'll crash at runtime and you give it the wrong type. So LLVM itself does not have any restriction as to what language you implement with it. The language I implemented is a dynamically typed language. I don't have any type definitions, and nor did I implement a type checker. So yeah, you can implement any dynamically typed language or statically typed language. Either both will work fine. It's not an issue.
Okay, does that answer your question? Okay. Any more questions? We will have like one last question. Okay, I guess. No? Okay. Yeah, thank you.
All right, thanks.